For over a century, physicists have been captivated by black holes, with the idea gaining momentum around 1916. These cosmic phenomena are among the most fascinating and perplexing mysteries we know, sitting at the intersection of immense gravitational forces and an unusual invisibility that challenges our understanding. A black hole, possibly weighing as much as 2 to 4 million times the mass of our Sun, remains a baffling presence in the universe. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by Michio Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information opens doors to deeper investigations into what may have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within. The universe is vast and awe-inspiring. But what exactly are black holes? Before we dive into Kaku's latest findings, it's essential to revisit the fundamental understanding of black holes. While most of us have a general sense of what a black hole is, some key aspects remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At the time, the concept was purely theoretical. It wasn't until about 50 years later that evidence confirmed black holes as real objects in space. This discovery came in the 1960s during studies of the star X-1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not only fluctuating randomly, but also being pulled into a dense, invisible mass. This mass, later identified as a black hole, transformed our perception of the universe. The discovery was groundbreaking, as it proved that black holes were not figments of Einstein's imagination, but tangible, elusive entities worthy of further investigation. Following this monumental discovery, scientists worldwide launched a global effort to uncover more about black holes. Their research led to the realization that the Milky Way alone might contain around 100 million black holes. However, due to the difficulty in detecting them, this estimate remains uncertain. Even though black holes are incredibly challenging to pinpoint, scientists believe that millions of these massive objects are hidden within our galaxy, making it even more crucial to understand them. The core concept, gravity. Black holes exert such immense gravitational forces that anything entering their vicinity is pulled into a singularity, a point where the known laws of physics cease to function. In simpler terms, black holes act like giant vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become part of the singularity, their body torn apart by intense gravitational forces before reaching the point of complete annihilation. It's best to avoid getting too close to one. However, they are scattered across the universe, with the nearest black hole being nearly 500 light-years away. A historic breakthrough. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of countless nights spent taking photographs and aligning them to create a single, cohesive image. As more data was collected, researchers discovered that black holes consist of 3 distinct layers, contradicting the common misconception that they are simply vast voids. 1. The event horizon. This marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. 2. The photon sphere. This is where light itself gets trapped, unable to escape due to the immense gravitational forces at play. 3. The singularity. Everything that enters the black hole is compressed into an infinitely small point, where the very fabric of reality collapses and the known laws of physics break down. What's even more intriguing is that each black hole is unique in its own way. While they follow the general 3-layer structure, their behavior can vary significantly. This makes them especially challenging to study, as conventional scientific methods do not apply to black hole research. Scientists must rely on indirect methods, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole would be futile, as anything crossing the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. This inevitable fate means that billions of dollars cannot be spent on experiments that would be destroyed before providing any useful data. As a result, researchers are left to study black holes in 2 dimensions, despite them being 3-dimensional singularities. The complexity of black hole research. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, scientists must account for the breakdown of physics as we know it. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. As a star burns its fuel, it can no longer generate enough energy to counteract the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter forms a singularity. To better understand black holes, NASA scientists turned their attention to the center of the M87 galaxy. There, they observed a powerful vortex of hydrogen gas spinning at astonishing speeds of 1.2 million miles per hour. The sheer force should have caused this gas to fly apart, yet it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to be up to 3 billion times the mass of our Sun. Theoretical advances, rotating black holes and wormholes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the behavior of rotating black holes. He proposed that, rather than collapsing into a single point as previously thought, a rotating black hole forms a thin, ring-like structure known as the ergosphere. This spinning disk of matter is crucial to understanding the breakdown of physical laws in the vicinity of black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time, connecting distant regions of the universe or even parallel universes. To grasp the concept of a wormhole, it's important to understand space-time as described in Einstein's theory. Space-time is a 4-dimensional fabric that is warped by objects with mass. This warping creates gravitational fields that influence the motion of other objects. Imagine space-time as a sheet of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole. A passage through space-time could instantly connect distant locations. Although wormholes remain purely theoretical, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse quickly if they ever formed. The need for a unified theory. The quest to understand black holes and wormholes has led physicists to seek a unified theory, a framework that combines general relativity, which describes gravity on a large scale, with quantum mechanics, which governs the behavior of subatomic particles. Currently, these 2 theories are incompatible, creating a major gap in our understanding of the universe. One of the most promising approaches to bridging this gap is quantum gravity, an area of research that aims to explain how gravity behaves at the smallest possible scales. One well-known candidate for a unified theory is string theory, which suggests that fundamental particles are not point-like objects, but tiny vibrating strings that exist in multiple dimensions. Another approach, known as loop quantum gravity, proposes that space-time itself is quantized, meaning it is made up of discrete units rather than being continuous. Hawking radiation, a black hole's glow. In 1974, physicist Stephen Hawking made a groundbreaking discovery that revolutionized our understanding of black holes. He proposed that black holes are not completely black. Instead, they emit a faint radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, suggests that black holes slowly lose mass and can eventually evaporate over time. Hawking's work introduced the concept of the black hole information paradox, which challenges a fundamental principle of physics, the conservation of information. In classical physics, information about a system is never lost, even if the system changes form. However, if black holes eventually evaporate and disappear, What happens to the information about the objects that fell into them? Does it vanish? Or is it somehow preserved? The black hole information paradox. The black hole information paradox remains one of the biggest unsolved mysteries in physics. Some theories suggest that information is encoded on the event horizon, forming a holographic representation of everything that has fallen into the black hole. This idea, known as the holographic principle, proposes that the entire three-dimensional universe could be described by information stored on a two-dimensional surface. Recent research, including studies based on quantum entanglement and wormhole theories, suggests that black holes may not completely destroy information, but instead scramble and release it in ways we don't yet fully understand. If this turns out to be true, it could provide profound insights into the nature of reality itself. The future of black hole research. Advancements in technology, such as the Event Horizon Telescope (EHT), have allowed scientists to directly image black holes for the first time, as seen with the famous 2019 image of the M87 black hole. Future missions, including NASA's upcoming LISA Laser Interferometer Space Antenna, aim to detect gravitational waves from merging black holes, providing even more insights into their structure and behavior. Additionally, projects like the James Webb Space Telescope continue to explore distant galaxies, searching for evidence of supermassive black holes and their role in the evolution of the universe. Could black holes be gateways to other universes? One of the most speculative yet intriguing ideas is that black holes might serve as gateways to parallel universes. According to some interpretations of quantum mechanics and general relativity, falling into a black hole might not lead to destruction, but instead to another region of space-time, possibly even another universe. This idea is linked to the concept of wormholes, which, if stable, could theoretically allow travel between different points in space and time. While no evidence of traversable wormholes has been found, ongoing research continues to explore the possibilities. Conclusion. Black holes remain one of the most mysterious and exciting subjects in modern physics. From their immense gravitational pull to the possibility of wormholes and quantum mysteries, they challenge our deepest understanding of space, time, and reality itself. As scientists continue to push the boundaries of our knowledge, we may one day unlock the secrets of black holes, perhaps even finding ways to harness their power or uncovering hidden pathways through the cosmos. Until then, black holes remain a reminder of how much there is left to discover in the vast and enigmatic universe. Alluded to as the hypothesis of everything is a journey that numerous physicists, including famous researcher Michio Kaku, have sought after for quite a long time. One promising contender for this hypothesis is superstring hypothesis, which suggests that subatomic particles are actually minuscule vibrating strings. The hypothesis proposes that these strings create the universe's texture, making sense of gravity, as well as the peculiarities surrounding dark openings and wormholes. However, superstring hypothesis also requires the presence of additional dimensions of space-time that are so small they are difficult to recognize with current technology. Regardless of the challenges, the quest for understanding dark openings, wormholes, and the texture of space-time continues to charm researchers, offering the potential for momentous revelations that could reshape our understanding of the universe. Going on from where we left off, the quest for superstring hypothesis and other theories that aim to unify the forces of nature is an ongoing challenge. Yet, it holds the promise of unlocking new insights into the very nature of reality itself. These theories suggest that the universe is composed of more than the familiar three dimensions of space and one of time. In fact, they propose that extra dimensions exist, but they are so tiny and compact that we cannot observe them directly with current technology. However, their existence could provide the key to understanding phenomena like dark openings, wormholes, and the deepest secrets of the universe. Superstring hypothesis offers an intriguing image of the universe, suggesting that all matter and forces are manifestations of minuscule vibrating strings. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle, just as a guitar string can produce different musical notes based on how it vibrates. The fundamental particles of nature could relate to different vibrational patterns of superstrings. If proven, this hypothesis would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the structure of the universe. This could potentially provide answers to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for the majority of the universe's mass and energy, yet remain largely mysterious. Yet, despite its elegance and promise, superstring hypothesis remains unproven. One of the major obstacles in testing the hypothesis is the fact that the additional dimensions it predicts are so microscopic that they are beyond our current observational capabilities. To detect these dimensions, we would require instruments of unprecedented sensitivity and precision. And even then, the evidence might be indirect. This makes superstring hypothesis a challenging subject to test through traditional scientific methods. However, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other approaches that could lead to breakthroughs in our understanding of dark openings. For example, quantum gravity is another field of research that seeks to unify the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of massive objects like planets, stars, and dark openings. The hope is that by combining these two theories, researchers can gain a clearer understanding of how gravity operates at the quantum level and, in turn, gain deeper insights into the nature of dark openings and other cosmic phenomena. The convergence of quantum mechanics and general relativity is particularly crucial when studying dark openings, as the extreme conditions near a dark opening's event horizon, where gravity is incredibly intense, demand a theory that can account for both quantum effects and relativistic effects. In fact, the interior of a dark opening, where the singularity exists, is one of the most perplexing and extreme environments in the universe. The singularity represents a point where space-time becomes so distorted that the usual laws of physics break down, and understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has led to the development of ideas such as loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and provide a more complete picture of dark openings. As we continue to explore the mysteries of dark openings, one thing is certain. The more we learn, the more we realize how much there is still to discover. Dark openings are not just points of destruction. They are also places of incredible complexity and potential. Whether they are gateways to other dimensions, as some theorists believe, or whether they hold the key to understanding the deepest mysteries of space-time, dark openings remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be refining our methods for observing and studying dark openings. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of dark openings. By detecting and analyzing these waves, scientists can learn about the behavior of dark openings and other celestial objects in ways that were previously unimaginable. The discovery of gravitational waves has already provided groundbreaking insights into the dynamics of dark opening mergers, and future studies are likely to yield even more discoveries. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which produced the first-ever image of a dark opening in the M87 galaxy, is an example of how innovative technology can shed new light on dark openings. By combining data from multiple radio telescopes worldwide, the EHT was able to capture an image of a dark opening shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to advance, we will likely be able to observe dark openings in even greater detail, revealing more about their structure, behavior, and role in the cosmos. The study of dark openings is not just about understanding these strange objects in isolation. It is also about uncovering the fundamental workings of the universe. Dark openings are essential to our understanding of space-time, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves, but also about the laws that govern the universe at its most extreme scales. The future of theoretical physics and the search for a unified theory. As we push the boundaries of modern physics, the quest for a theory of everything continues to drive scientific inquiry. Superstring theory remains one of the most promising candidates for a unified theory, but it is not without its challenges. Some physicists argue that string theory lacks direct experimental verification and may be difficult to test with current technology. This has led to the exploration of alternative approaches, including loop quantum gravity, LQG, and other quantum gravity models, each offering different perspectives on the nature of space-time at the most fundamental level. One of the biggest hurdles in modern physics is bridging the gap between quantum mechanics and general relativity. While quantum mechanics successfully explains the behavior of subatomic particles, and general relativity accurately describes gravity and large-scale cosmic structures, the two theories are fundamentally incompatible under extreme conditions, such as within black holes or at the Big Bang singularity. Any successful theory of everything must reconcile these discrepancies, exploring extra dimensions and multiverse hypotheses. If superstring theory is correct, the universe may consist of more than the four dimensions, three of space and one of time, we are familiar with. Instead, it suggests that additional spatial dimensions exist, but they are compactified or hidden at scales too small to be observed directly. These extra dimensions could explain some of the biggest mysteries in physics, such as why gravity is so much weaker than the other fundamental forces. Some versions of string theory suggest that our universe may be just one of many in a multiverse, a vast collection of parallel universes with different physical laws and properties. This idea, though speculative, has gained traction through studies in cosmology and quantum mechanics, particularly in the context of the many-worlds interpretation of quantum physics and the concept of cosmic inflation. If the multiverse is real, it could have profound implications for our understanding of reality. It might help explain the fine-tuning of the physical constants that make life possible in our universe. Instead of being a unique and precisely tuned cosmos, our universe may simply be one of many, with different universes having different laws of physics. Black holes as laboratories for new physics. Black holes offer a natural testing ground for many of these advanced theories. In particular, studying the event horizon and the information paradox could provide crucial insights into the nature of space-time and quantum gravity. The black hole information paradox, first proposed by Stephen Hawking, arises from the apparent contradiction between quantum mechanics and general relativity. According to Hawking's calculations, black holes emit radiation, now known as Hawking radiation, and gradually lose mass over time. However, if a black hole evaporates completely, what happens to the information that fell into it? Quantum mechanics dictates that information cannot be destroyed, yet general relativity suggests that it might be lost forever. Resolving this paradox could lead to groundbreaking new physics. Some proposed solutions involve the idea of holography, where information is not lost, but rather stored in a lower dimensional surface, akin to a holographic projection. This concept is central to the holographic principle, which suggests that the entire universe might be describable as a lower dimensional system, challenging our traditional notions of space-time. New technologies and the future of observation. Recent technological advances, such as the Event Horizon Telescope, EHT, and the detection of gravitational waves, are revolutionizing our ability to observe and study black holes. Future missions, including space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, will allow scientists to explore black hole mergers with even greater precision. Additionally, advancements in quantum computing and particle physics experiments, such as those conducted at the Large Hadron Collider, LHC, may provide indirect evidence for extra dimensions, new particles, or even string vibrations. The discovery of supersymmetry, SUSY, if verified, could lend strong support to string theory by demonstrating the existence of previously unknown fundamental particles. Conclusion: a new era of discovery. The search for a theory of everything represents one of the greatest intellectual challenges in human history. Whether through string theory, loop quantum gravity, or yet another undiscovered framework, physicists continue to push the limits of our understanding. Black holes, extra dimensions, and the fabric of space-time itself hold the keys to unlocking these mysteries.